All right, hello and welcome back. Today I'm going to do a little bit of applying the gamma distribution. And the key thing to remember about the gamma distribution is that it's a generalization of the exponential distribution. And because the exponential distribution is the sort of tied together with the Poisson, part of the Poisson process, and tied together with the Poisson distribution, that means the gamma. And so the gamma distribution will have the same properties. So the gamma, so this is the Greek letter, capital letter for gamma. So this is what I mean when this is the symbol we'll use when I say gamma. And the general distribution is, let's use a different random variable, t. Of course, it doesn't matter, but sometimes we just use t because all these problems, well, not this example I'm going to use, but many of these problems measure time. It doesn't have to, of course, it's just a variable. All right, so t is gamma r lambda. Okay, so now the lambda here is the same lambda from exponential function, okay? And the same lambda, well, not exactly this. It could be the same lambda also with the Poisson process. However, if you recall, when we were doing the Poisson process, depending on what time measurements we used, lambda would change, right? So when we're using the exponential function, basically you usually use the unit, a unit rate, okay, of lambda. So that's kind of more standardized. And so this will also be a unit rate when we're talking about the gamma function. Now this part here is just saying how many events, or in this specific case, and by the way, I'm reusing a problem that I did before on exponential functions just to keep the continuity here. So we have the same thing. There's an exponentially distributed distribution of flaws along the length of a cable. So the length of the cable is continuous, and we're trying to measure, we also know the mean of this, 1/12, so I did some problems on this before. But what's changed now is I'm not looking for just one flaw or the distance between two flaws. I'm looking for the distance basically between two flaws, or how long, or sorry, four flaws. I'm looking for the distance between four flaws, and that will be represented by my random variable. Okay, so this r is just this number here. How many? Now, no, there's a very close connection between, this is the sort of the continuous version of the negative binomial. So in the negative binomial, if you recall, there's a r here too, and then the little p, and that was a generalization of the geometric distribution. And for the geometric distribution, this was 1. And so we didn't have to write it when we used the geometric equation for this. But this is the same case here. So if r was 1, then we would have an exponential distribution. We have basically be the same questions, same distributions that I dealt with in the problem before on exponential function. Okay, so in this case, r is 4. So let's fill out t for this specific problem here. T is gamma r. R is 4. And lambda is, well, you can refer, lambda is 1/12. If you've forgotten that this comes from a little side fact that the mean equals 1/lambda. And this is the mean here. We're given that. So we find lambda using this little formula here. Now note, this lambda is not the average for 4 flaws. This is the average for 1 flaw. So this is the same lambda from the exponential version of the problem where there's just 1. But this 4 over here, this gamma and this 4 over here, telling us that it's not exactly an exponential function. We're worried about how many, the time it's going to take, or in this case, the distance it's going to take for 4 flaws. Okay, so maybe, and let's write some stuff out so we know what t represents. So t represents the time takes, or sorry, not time, the distance. Oh, now I'm that mistake is fair because, like I said, these problems often involve time, and it's kind of good though that we have this problem just to note that it doesn't have to. Just very common that it is time, but it could be any continuous variable down here. In this case, distance. It takes 4 flaws. And when with, let's say, with unit, that's really bad spelling, with the unit rate (1 over 12). So there's like, there's 1/12 flaws per meter, you could say. Okay, that's one way to look at where this 1/12 is coming from. And when, if there's 1/12 per meter, and there really isn't, that's just an average. But if there was, then the mean it would take for 1 flaw would be 1 meter. So that's where your lambdas comes in. Okay, so we're gonna flip this around, and we're gonna introduce a new variable process. So we're concerned. We're looking for the probability that t is less than, or it could be equal to 25 meters. Okay, so the probability that there's 4 would be the probability that t is less than 25. Okay, that's what we're looking for. But instead of going, now I will give you a formula at the end of this where you could solve for this directly. However, in order to show where that formula is coming from, and also just a good practice to see the connections going on here with the other distributions, is that what I'm going to do is I'm going to introduce a new variable, and let's use let x be a random variable. So I'm just going to use a common abbreviation for that. Be a random variable of how many flaws in 25 meters. Okay, so notice I've fixed my distance here. I'm rephrasing this basically as a Poisson distribution. So this is the Poisson flip side, Poisson version, but it's fixed for specifically when we're looking at 25 meters. Okay, not Poisson is going to depend, so the lambda will change depending on what this value is here, what distance I'm looking for, or in many cases, how long a time frame I'm looking at. Okay, so because I'm looking at 25 meters and the unit rate is 1/12, the amount that I would expect, so my other lambda, my Poisson lambda, let's to distinguish this, let's call it lambda little x, is going to be, well, now I wish I had changed this to 24 meters, but let's just stick with it. Reality is usually not nice anyway. So this is my lambda. Now let's be clear. This is the lambda for the Poisson process that involves this. So remember, a Poisson process is all about how many events occur in a fixed time. And what we're doing is, because in this problem, or fixed time or fixed distance, in this problem, where fixed distance is 25, and we're concerned about how many flaws there are going to be in that distance. So what I'm going to do is I can remodel x is Poisson 25 over 12. Okay, let's round it off to 2.1. Okay, so where did this come from? Comes from how many we expect, the average amount we expect over 25 meters. So the average we expect over 25 meters is going to be approximately 2.1. And this is going to model the underlying Poisson process here. And now we can reformulate this. So we are concerned about there being 4 flaws in this. More probability that that would actually happen. Well, that's the same as the probability that, so this is the same as the probability that x is greater than or equal to 4. So this is saying that in 25 minutes there were 4 or more flaws. And that would be equivalent to this t, which represents 4 flaws, the distance in 4 flaws. That would be the same as this being less than 25 meters. So this is the key way to look at this problem in order to get the equation or understand where the equation is coming from. Okay, so the important information we had from the last slide, key information, is that this is an equivalent statement to this, and that x is Poisson approximately 2.1. Okay, so this is a good review of our Poisson distribution and how we would solve a problem like this. So p x greater than or equal to 4. It's been a while since we did this, but the trick here is that, well, we don't have a cumulative distribution function, unfortunately, for Poisson, a nice one like we did for, we do for most of these continuous distributions. But what we did was we switched it. Here we flipped this part. And because this is discrete, the only values between, there's no values between 3 and 4. So if you union this one, p x less than 3 and x less than 4, or sorry, x greater than 4, then you would have the whole, all the possible values of x. So if we subtract that, we get these two are complements, and this is the relationship between complements. Okay, and sadly, there is no real shortcut formula here. What we do is we just break this up into all the values. Now, remember, in a Poisson process, the smallest value x can take is 0. So this, but it only takes on discrete values. So we can actually just list all these out. So x equals 2. And lastly, and fast forwarding here, we end up with this expressions down here. Now note, for each of these little expressions here, these are just the Poisson formula. The formula for the Poisson when x equals 0. Formula and lambda equals 2.1. Same thing here. Each of these are just plugging in the formula. So that's kind of tedious, and I know you could get out your calculator now and work this out.